Think about how often you check the weather. Like multiple times a day,
Oh,
probably.
absolutely. It's almost second nature for most people now.
Yeah, exactly. Just that quick glance at your phone. Do I need a coat? Umbrella.
And it goes way beyond that, doesn't it? Big industries, they make huge decisions based on forecasts.
Billion-dollar decisions sometimes.
Right.
Agriculture, aviation, energy. So much hinges on knowing what the weather's likely to do.
And it's funny, you see that little sun icon or the cloud with raindrops, and it seems so simple. But underneath that,
Yeah.
it's actually incredibly complex.
It really is. That straightforward prediction, sunshine or showers, it's the end result of this vast, intricate system. Observations, complex science, powerful computers. It's quite a mix.
Right. So that's what we want to do in this deep dive, kind of pull back the curtain on weather forecasts.
Sounds good. Where should we start?
Let's get into everything from, the basics, what information are they really giving us, to the more advanced stuff, the tech behind it all. We'll be your guides, basically, navigating through the essentials. Okay, so first things first. Beyond just hot or cold, wet or dry, what is a forecast actually telling us? What's packed into that prediction?
Well, fundamentally, it's predicting how the atmosphere is going to behave over a certain time in a certain place. And yet, it's more than just temperature.
Right.
You get specific about, like, the type of precipitation. Is it rain? Is it snow? Sleet? Maybe even hail?
And cloud cover, too, presumably.
Exactly. Clear skies, partly cloudy, mostly cloudy, totally overcast. And then, of course, the highs and lows for temperature, wind speed, wind direction, sometimes even gusts, those sudden bursts.
And knowing all that detail.
Yeah,
It's really about being prepared, isn't it? Making better decisions.
totally. It empowers you. Simple stuff, like grabbing that umbrella, but also bigger things, a farmer deciding when to plant based on expected rain or temperature trends.
Or knowing if you need to worry about frost overnight for your garden.
Exactly. Or, planning a hike and seeing if thunderstorms are likely. Construction crews needing to know about high winds. It lets us plan around the weather, not just react to it.
That makes sense. So, okay, you mentioned observations earlier, this vast network. Where does all this foundational data actually come from? Let's start with weather stations. We see them around. What are they doing?
Think of them as like checkup points for the atmosphere, constantly taking its pulse right there on the ground.
Okay. Pulse like temperature, humidity.
Yep. Temperature, humidity, that's the moisture in the air pressure, how it's changing, wind speed, wind direction, all measured continuously at that specific spot.
So very localized information, but lots of locations feeding in.
Exactly. And even though it's local, it forms the bedrock for the bigger picture predictions. It's like the ground truth.
Ah, a reality check for the computer models later on.
Precisely. It keeps the models honest in a way. But you're right, it's based on where the stations are. There are gaps, especially over, say, big oceans or remote land areas.
Right, which must be a challenge for getting a truly global picture. So that leads us to looking up, I guess. Satellites, they must offer a completely different perspective.
Oh, absolutely. A game changer. Satellites give us that continuous wide-angle view from space. They see the big picture developing.
Like massive storm systems, hurricanes forming over the ocean.
Exactly that. Huge cloud formations stretching across continents, things you just can't grasp from the ground. They can track hurricanes, monitor their intensity, their path.
So like an early warning system for the really significant stuff.
Definitely. And they're crucial for filling in those data gaps we mentioned. Over the oceans, deserts, polar regions, places where ground stations are few and far between. Satellites give us data from there.
What kind of data beyond just images of clouds?
Lots. They can measure sea surface temperatures, ice cover extent, even infer temperatures and moisture at different levels in the atmosphere using infrared and microwave sensors. It's pretty sophisticated stuff.
Wow, okay. So ground stations for the surface details, satellites for the big picture, and remote areas. What about weather balloons? They go up through the atmosphere, right?
Yeah, they provide that crucial vertical slide. They carry instrument packs called radiosondes, way up high. And as they rise, they're measuring temperature, humidity, air pressure at all these different altitudes.
Ah, okay. So not just surface level, not just the view from the top, but what's happening throughout the layers of air.
Exactly. And often they're tracked by GPS too, so we get wind speed and direction at various heights as well.
Why is that vertical information so important?
It's absolutely key for understanding atmospheric stability. Is the air likely to rise and potentially form thunderstorms, or is it stable? It also helps track the movement of things like cold fronts and warm fronts through the atmosphere, not just along the ground. This upper air data is vital input for the computer models.
Got it. So stations, satellites, balloons, all feeding data into the system. Now let's talk temperature again. Forecasts always give a high and a low. Pretty basic, but what's the real significance there?
Well, the high is usually the warmest point expected during the day. Typically happens in the afternoon after the sun's had time to heat things up.
And the low?
That's the coolest point, usually overnight or maybe just before sunrise, after the ground has radiated heat away all night.
And just knowing that range, that swing,
Right.
that helps us plan.
Absolutely. It tells you if you need layers, right? A big swing means you might start cool, get warm, then cool off again. It helps plan activities, too.
Yeah.
Like you said, protecting plants from a potential overnight freeze if the low is dropping significantly. Yeah. It's the difference, the range, that's often as important as the numbers themselves.
Makes sense. Okay, now forecasts cover different time spans. We get hourly ones, daily ones, weekly, even longer sometimes. How does the accuracy hold up as you look further out?
Yeah, that's a really important point. The short-term forecasts say the next few hours, up to maybe 48 hours, those tend to be the most accurate.
Why is that?
Because they're dealing mostly with weather systems that already exist, things we can see on radar and satellite, things we're tracking. The models are predicting the movement and evolution of stuff that's already formed.
So they can be more specific.
Exactly. You get more detail. Hourly temperatures, better timing on rain starting or stopping, wind shifts, cloud descriptions like, clearing by midday or showers developing late afternoon. That's the stuff you use for your immediate decisions.
Okay. And then the longer term, say a week out or even months.
Right. As you look further ahead, a week, a month, a season, the accuracy definitely decreases. It's just the nature of the atmosphere. It's technically a chaotic system.
Chaotic, meaning small changes can have big effects down the line.
Precisely. Tiny uncertainties in the initial measurements can get amplified hugely over time. So long-term forecasts become more about general trends, probabilities.
Less specific, more like tendencies.
Yeah. You'll hear things like temperatures likely above average next month or potential for below normal rainfall this summer. Useful for big picture planning, maybe for farmers or planning a vacation way in advance, but you wouldn't bet on the exact weather for a specific day weeks out. You always need to check back closer to the time.
It really highlights how complex and, well, fundamentally unpredictable the atmosphere can be beyond a certain point.
It's a constant challenge for meteorologists trying to push that accuracy window further out. Okay, so we've covered the data sources, stations, satellites, balloons, and how accuracy changes over time. Now, how does all that raw data actually get turned into a prediction? What are the tools?
Right, the transformation process. This involves some really powerful technology and analysis. A key tool, one people are probably familiar with, is weather radar.
Yeah, those maps with the colorful blobs moving around,
Yeah.
green, yellow, red.
Exactly, but what's it actually doing? Radar works by sending out pulses of energy, microwaves.
Okay.
When those pulses hit precipitation, raindrops, snowflakes, hailstones, some of that energy bounces back to the radar antenna.
Like an echo.
Precisely. By analyzing how long it takes for that echo to return, how strong it is, and crucially, with Doppler radar, how the frequency of the wave has shifted.
Doppler. Like the Doppler effect for sound, but with radio waves.
Exactly the same principle. That frequency shift tells us whether the precipitation is moving towards or away from the radar, and how fast.
So you can see the movement within the storm.
Yes, and that's vital. It helps identify rotation in thunderstorms, which is a key indicator for potential tornado development. The strength of the return signal tells us the intensity: light rain, heavy rain, hail. So radar gives location, intensity, and movement of precipitation in real time.
So those colors do mean something specific. Intensity, basically.
They're calibrated to represent different precipitation rates. It's crucial for tracking storms as they happen and issuing immediate warnings, like for flash floods or severe thunderstorms.
Got it. And satellites, we touched on them giving the big view. How do they feed into the detailed forecasting process beyond just the pictures?
Well, those satellites aren't just taking photos, they are constantly gathering quantitative data, measuring things like the temperature of cloud tops, which tells us how high they are, the amount of water vapor at different atmospheric levels, ocean surface temperatures, a whole suite of measurements. And this detailed data is fed directly into the computer models. It provides the starting point, the initial conditions, especially over those vast ocean areas where ground data is sparse. It's not just seeing, it's measuring.
Right. Which brings us to the computer models themselves. These sound like the real heavy lifters.
They absolutely are. Think of them as incredibly complex digital simulations of the entire Earth's atmosphere.
Wow.
They take in all that data we've talked about from stations, satellites, radar, balloons, billions of data points. That creates the initial snapshot of the atmosphere's current state. Then the models use fundamental laws of physics equations governing fluid motion, heat transfer, how moisture behaves, to calculate how that state will change over time. Step by step, predicting temperature, pressure, wind, humidity into the future.
Like fast-forwarding the atmosphere.
In a computational sense, yes. It requires immense processing power. We're talking supercomputers, some of the biggest in the world, running these calculations.
I can imagine.
This allows us to predict large-scale weather patterns, storm development, track weather systems across continents. Absolutely essential for modern forecasting and warnings. But again, they're simulations, not perfect crystal balls, especially further out in time. There's constant work to improve them.
And the weather balloon data, that vertical slice, how does that fit into the models?
That vertical profile data, temperature, humidity, wind at different heights, is directly assimilated or plugged into the models. It gives a much more accurate three-dimensional starting picture.
Makes the initial snapshot much more complete.
Exactly. Knowing how temperature changes with height, for instance, is critical for predicting things like thunderstorms or inversions. It adds essential detail that you can't get just from the surface or from satellite views alone.
And the global network of stations. Having more of them helps how?
A denser network means a more detailed, higher resolution picture of current surface conditions globally. This improves the accuracy of the initial state for the models, which translates into better short-term forecasts, particularly for more localized weather features. And this data is shared internationally almost instantly. It's a huge collaborative effort.
Supercomputers doing the number crunching. It sounds like they're indispensable.
Couldn't do it without them. Processing the sheer volume of data, running the models themselves within a useful time frame, it all relies on massive computational power. They also allow researchers to test new model versions and improvements.
Okay, one more data source. You mentioned historical data. How does looking at past weather help predict future weather?
It's about understanding climatology, the typical weather patterns for a place at a certain time of year. By analyzing decades of records, meteorologists identify probabilities.
Like knowing that July is usually the hottest month, or March is often windy.
Exactly. Or knowing the average date of the first frost, or the typical track of storms during a certain season. It doesn't predict a specific event, but it provides context. It helps make more informed probabilistic forecasts by knowing what's normal or likely based on past behavior, learning from history, essentially.
So it adds another layer of understanding, even if the atmosphere always has surprises. It's just fascinating how all these pieces, observations, physics, computing power, historical context come together. But okay, the forecast is made. Now we have to understand it. Let's decode some key terms.
Good idea, because a forecast isn't much use if the terms are confusing. We've done temperature highs, lows, Celsius, Fahrenheit. What about precipitation? There's rain, snow, sleet, hail.
Right, and then chance of rain.
Yeah.
What does that percentage actually mean? I feel like people misunderstand that one a lot.
That's a common one. Precipitation itself is just any water falling from the sky, liquid rain, frozen snow crystals, sleet, which is like frozen raindrops or pellets, and hail, which are larger ice chunks from thunderstorms. Now, that chance of rain, say 40%, it means that at any specific point within the forecast area, there's a 40% probability of measurable precipitation occurring during the forecast period. It's probability X area. So it doesn't mean it will rain over 40% of the area or for 40% of the time, just that your specific spot has a 4 out of 10 chance of getting wet.
Oh, okay. That's clear. Probability at any given point.
Yeah.
And rainfall amounts, like millimeters or inches.
That's the predicted total accumulation if precipitation does occur, how much water will end up in the rain gauge.
Got it. What about humidity? We know it makes it feel sticky, but what is it?
Humidity is just the amount of water in its gas form present in the air. Relative humidity, the percentage you usually hear, compares the actual amount of water vapor to the maximum amount the air could hold at that specific temperature.
So 100% relative humidity means the air is totally saturated, like fog.
Exactly. And high humidity makes it harder for our sweat to evaporate, which is how we cool down. So hot temperatures feel even hotter and more oppressive. That's the feels like temperature or heat index.
And low humidity, can that make cold feel worse?
It can, yeah. Dry air allows moisture to evaporate more quickly from your skin, which has a cooling effect, making cold air feel even chillier.
That feels like number is definitely useful. Okay, clouds. Clear, partly cloudy, mostly cloudy, overcast. Those seem fairly straightforward.
They are, generally. Clear means negligible cloud cover. Partly cloudy means some clouds, but still significant sun. Mostly cloudy means more clouds than sun. And overcast means the sky is completely covered, usually looking gray and uniform. Gives you a visual expectation.
Right. And wind, speed and gusts.
Wind speed is how fast the air is moving horizontally, usually in kilometer or descriptive terms like light, moderate, strong give a general feel. Gusts are important. Those are sudden, brief surges in wind speed that can be much higher than the average or sustained wind.
So winds 25 kilometer gusting to 40 means it's mostly 25, but watch out for sudden bursts up to 40.
Precisely. Those gusts can be what cause problems, like making driving difficult or blowing things around.
Makes sense. One more. Barometric pressure. Low pressure means storms. High pressure means nice weather. Why?
So barometric or atmospheric pressure is literally the weight of the column of air above you. Low pressure generally happens when air is rising. Rising air cools, condenses moisture, forms clouds, and can lead to precipitation and storms.
Okay.
High pressure is the opposite. Air is sinking. Sinking air warms and dries out, preventing clouds from forming. So high pressure usually brings clear skies and stable conditions. When you hear a low pressure system is approaching, that's the heads up for potentially wet or stormy weather.
Understanding that really helps interpret the why behind the forecast sometimes. It's like learning the language of weather. Okay, so we know forecasts come in different types, different time frames. Can you break down the main ones?
Sure. You've got your short-term forecasts, generally up to about 48 hours. These are the most detailed, best for immediate decisions, what to wear today, planning an outing tomorrow. Specifics on temps, rain timing, wind, clouds, often hourly breakdowns.
Right, the day-to-day planning ones?
Yeah.
Then what?
Medium term, typically looking out 3 to 7 days, these give a broader overview. General trends and temperature warming up, cooling down likelihood of significant rain or snow systems moving through. Good for planning a weekend trip or an event a few days out. Less precise than short term, but gives you a good heads up.
More of a general trend guide for the week ahead.
Exactly. Then you have the long-term forecasts. Weeks, months, even seasonal outlooks. As we said, these are much less certain. They talk about broad patterns, above average temperatures expected this spring, drier than normal summer predicted. Useful for very large-scale planning, like in agriculture or maybe for very flexible long-range travel ideas. But you absolutely need to check shorter-term forecasts closer to the time. Treat them as possibilities, not guarantees.
Okay. And then there's a really critical category. Severe weather alerts.
Yes, absolutely crucial. These aren't standard forecasts, they're specific alerts for dangerous conditions. Warnings mean a threat is imminent or occurring: tornado warning, hurricane warning, blizzard warning, flash flood warning. They demand immediate action to protect life and property.
And advisories.
Advisories indicate conditions that are less dangerous but still potentially hazardous or inconvenient, like a frost advisory, a heat advisory, dense fog advisory. They mean you should be aware and take appropriate precautions. These alerts always give specific info: the threat, location, timing, potential impact, and safety advice. Pay very close attention to these.
Definitely. Don't ignore those warnings or advisories. It seems clear that understanding all this is way more than just convenience. What's the bigger picture impact?
Oh, it's massive. Start with safety. Timely warnings for hurricanes allow evacuations. Tornado warnings give people precious minutes to shelter. Winter storm warnings help people avoid dangerous travel. Even day-to-day, knowing about heat waves or sudden cold snaps helps prevent health issues. It literally saves lives.
And the economic side.
Huge. Agriculture depends on it for planting, harvesting, protecting crops. Aviation needs it for safe flights, avoiding storms and turbulence. The energy sector uses forecasts to predict demand, how much heating or cooling will be needed, and also to manage renewable sources like wind and solar, which are weather dependent. Construction, shipping, tourism, retail. Countless industries are impacted and make decisions based on forecasts.
It touches almost every part of the economy. What about environmental aspects?
Yeah, managing water resources is a big one. Reservoir levels, drought management, flood prediction all rely on rainfall forecasts. Predicting extreme events also helps prepare for environmental impacts, like increased wildfire risk during droughts or potential landslides after heavy rain. It helps us anticipate and sometimes mitigate environmental damage.
And thinking even bigger, globally.
Studying global weather patterns is fundamental to understanding climate change. Tracking large-scale phenomena like El Niño or La Niña helps us understand interconnectedness, and international sharing of weather data is vital for disaster response coordination around the world. It fosters cooperation.
It really shows how interconnected everything is.
Mm-hmm.
Science, technology, safety, economy, environment, global cooperation, all reflected in something we check every day. So for listeners trying to make sense of their daily forecast, what are some practical takeaways? How can we listen better?
Okay, some practical tips. First, just pay attention actively. Don't just glance. Note the high and low temperatures. Make sure you know if it's C or F.
Good point. Easy to mix up if you travel.
Definitely. Look at the chance of precipitation. Remember what that percentage means. Note the wind speed, and especially if gusts are mentioned. Consider the humidity, and that feels like temperature.
The comfort factor.
Exactly. And crucially, heed the warnings and advisories. Take them seriously. If you need specifics for a certain time, check the hourly forecast if it's available.
Hourly is great for timing walks or errands.
Mm-hmm. And remember, treat those longer-term forecasts as general trends, potential patterns. Always confirm with shorter-term updates as you get closer.
So be an active listener. Note the key details, understand the terms, prioritize warnings, and use the right forecast for the right time frame.
That sums it up pretty well. Maybe check a couple of different sources, too. Sometimes you get slightly different perspectives or timings, which can be informative.
That's a great tip, too. Okay, so wrapping up this deep dive, we've really covered a lot of ground, from the basic data coming from stations, satellites, balloons,
to the technology like radar and the incredible power of computer models, turning that data into actual predictions.
We've decoded terms like humidity and barometric pressure, looked at short, medium, and long-term forecasts, plus those vital severe weather alerts.
And highlighted why it all matters for safety, for the economy, for the environment, and even for global understanding.
Plus, hopefully given everyone some practical tips for getting more out of their daily weather check.
Well, it's pretty staggering. We all check our apps, sure, but pilots...
Oh, absolutely.
You can just imagine the critical need moment to moment for flight safety. It's not just avoiding a bit of bumpiness, it's navigating potentially, well, catastrophic conditions.
Precisely. The level of precision, the timeliness needed in aviation weather is just immense. I mean, even tiny deviations from what was predicted can have huge consequences.
Yeah.
They need to know about sudden wind shear or microbursts, those really intense localized downdrafts. Yep. They need that in real time for takeoff, landing, even changing flight paths midair.
Wow. And it's not just up in the air, is it? What about emergency response teams? Down on the ground.
Yeah, good point.
Like when a hurricane's making landfall or there's a sudden flash flood, they need a constantly updating picture, don't they, to deploy resources effectively and, safely. Lives are literally on the line with those insights.
Exactly. Without that near-instant understanding of, say, where the greatest need is, or which roads are suddenly impassable, or where things are just deteriorating really fast,
right,
emergency responders would be working at a huge disadvantage. Being able to see the weather as it evolves, minute by minute, allows for a much more targeted, much more effective response.
It even gets into industries you might not immediately think of, like shipping companies, navigating busy seas or treacherous waters, needing real-time data on waves and storms coming their way.
Definitely. And farmers, too.
Oh, yeah, farmers, making decisions almost minute by minute during planting or harvesting based on what's happening right then.
Yeah. Is it about to pour rain? Should they get the equipment in? That kind of thing. And even our energy providers, they rely on this to manage the power grid, anticipate potential blackouts from, severe ice storms or high winds. It's also interconnected.
It really is.
And what's really interesting there is how these different sectors are often using the same underlying data, but for completely different reasons. So a pilot's worried about wind shear near the airport runway, while the farmer nearby is looking at, like, hyper-local rainfall just over their fields. The real-time aspect lets them tailor that info.
Okay, so this brings me back to the big question I had. How do we actually see these dangerous, fast-changing events as they happen? What are the immediate eyes and ears tracking a storm as it, spins up?
Well, the absolute backbone of this real-time monitoring is that continuous stream of data. It comes from our established network. Weather radar, constantly scanning the skies.
Right.
Satellites giving us that crucial view from above, and all those ground stations dotted across the landscape, feeding in surface observations, temperature, wind, pressure.
All feeding in constantly.
Constantly. But the real key to understanding the real-time part, especially for those very short-term threats, is a technique called nowcasting.
Nowcasting. Okay, that sounds exactly like what it is focused on the now. What does that actually mean?
That's basically it. Nowcasting is very short-range forecasting. We're talking typically a window from just a few minutes up to maybe a couple of hours ahead.
Couple of hours max.
Usually, yeah.
Yeah.
It's specifically designed for those weather events that develop and move really rapidly. Things like intense thunderstorms, those sudden downpours that can lead to flash floods, or even, say, the rapid formation of dense fog.
Okay.
Think of it as giving you a highly localized, very near-term heads up.
So if a really nasty thunderstorm is brewing and it's heading straight for me, nowcasting is what gives me that immediate warning, like right before it hits.
Precisely that. It's that ultra-short-term prediction that lets people, and organizations too, take immediate action, protect themselves, protect assets.
And the tools for nowcasting, I guess they're all about watching what's happening right now and just projecting that forward a tiny bit.
Exactly. It's about observing and extrapolating in the very near term.
Like those vivid radar maps we see everywhere now.
Yes, high-resolution radar imagery is absolutely a cornerstone of nowcasting. It lets meteorologists track the movement and, crucially, the intensity changes within individual storm cells almost as they happen.
Right. You can see the reds and yellows getting brighter.
Exactly. You see the areas of heavy rain or hail. And Doppler radar, that's key too. It gives us information about the winds inside the storm. That can be critical for spotting rotation, potential tornadoes. That high resolution is what lets forecasters see the fine details needed for those short predictions.
And what about lightning? I've seen those maps too. It looks like they update constantly. How do they fit in?
Lightning detection network's another vital tool. They pinpoint exactly where lightning is striking, and they track how that pattern is moving or changing.
Okay.
So a sudden jump in lightning activity, or maybe a specific pattern of strikes, that could be a really strong indicator that a storm is rapidly intensifying, becoming more dangerous very quickly. It adds another real-time layer about the storm's sort of health.
And I guess all those weather stations on the ground are feeding their data in too, nonstop.
Oh, absolutely. Those automated stations provide continuous surface observations. Temperature, wind speed, wind direction, atmospheric pressure, rainfall amounts.
Basic stuff, but critical.
Critical in real time. Because rapid changes in those numbers, like a sudden pressure drop or a sharp spike in wind gusts, those can be telltale signs of a storm approaching or intensifying right overhead. So you combine that ground data with the radar, with the lightning information, and you start to get a very detailed, up-to-the-minute picture of what's happening. The whole idea, really, of nowcasting boils down to watching the storm as it forms and moves, using this whole suite of observational tech.
It's amazing to think about all those systems just working together, constantly feeding information in real time. That must explain why I get those storm alerts on my phone sometimes when I'm out.
Exactly. That's nowcasting in action.
It's predicting that a severe storm is about to hit my specific spot.
Precisely. Those alerts are often triggered by nowcasting analyses, identifying a significant threat coming your way within a very short time frame, maybe 15-30 minutes. Gives you that crucial window to seek shelter or change your plans.
Yeah, and I can really see how cities and towns would rely heavily on this. Like, if there's a risk of flash flooding from a sudden downpour.
Oh, hugely important for them.
Nowcasting would give them that immediate info they need to maybe close certain roads or issue urgent warnings to people in low-lying areas, right?
Absolutely. For public safety officials, it provides critical situational awareness. It allows for proactive decisions. Instead of just reacting after the floodwaters are already rising.
Yeah. Too late then.
They can take steps beforehand to mitigate the risks based on that very near-term forecast.
Even something maybe less dramatic, like a school deciding, okay, we need to cancel afternoon sports practice because severe weather is rolling in fast. That's all based on nowcasting, giving them that immediate heads up.
Precisely. It's all about using the most up-to-the-minute information to make informed decisions, prioritizing safety. And what's been really transformative, I think, is how much more accessible this kind of real-time weather data has become for us, just as individuals.
Oh, absolutely. It feels incredible that I can just pull out my phone and see a detailed animated radar map showing exactly what's happening nearby. That level of info used to be just for meteorologists, didn't it?
It really did. It's truly a game changer. That accessibility empowers everyone to make their own informed decisions about their activities, their safety. You see a storm coming, you decide, okay, maybe postpone that picnic or head indoors now.
And the fact that we now get those actual alerts pushed directly to our phones is huge. I mean, I remember having to actively tune in to the radio or TV weather report. Now, if there's a severe threat nearby, my phone just buzzes automatically.
That proactive delivery of critical info is such a significant advance. It ensures that even people who aren't, actively checking the weather are still alerted to potential dangers right where they are.
Yeah.
It's a vital safety net.
Okay, so we've got this incredible real-time monitoring, nowcasting happening right now. What's next? What does the future hold? Are there big technological leaps coming that will make this even better, more precise?
This is where things get really exciting. The big buzz right now is definitely around the integration of artificial intelligence, particularly machine learning, into weather monitoring and forecasting. It looks set to bring about a pretty significant transformation.
AI in weather forecasting. Okay, how does that actually work? That sounds a little bit like science fiction.
Well, it might sound futuristic, but it's becoming reality surprisingly quickly. Machine learning models, basically, are designed to analyze just enormous amounts of data, both historical weather patterns and real-time observations.
Okay.
And they can identify complex patterns much faster and often more accurately than traditional forecasting methods or even human analysts in some cases. These algorithms can sift through incredibly complex data sets and pick out subtle signals that might otherwise be missed.
So these AI systems are basically learning from like millions of past weather events to get better at predicting what's coming next.
That's the core idea, yes.
Mm.
They're trained on these massive historical data sets. It lets them recognize recurring patterns, understand the sort of complex relationships between different weather variables, temperature, pressure, humidity, wind, all interacting.
Wow.
And they learn to anticipate how weather systems evolve, hopefully with increasing accuracy over time. Think of it as a constantly learning, constantly refining expert system just for weather prediction.
That sounds like it could be incredibly useful for predicting those really severe, fast-developing things like maybe hurricanes or flash floods.
Absolutely. That's a major focus area. Imagine AI systems analyzing satellite images, radar data, ground observations, all in real time to give us even faster, more accurate warnings for these high-impact events.
More lead time.
Exactly. More lead time to prepare, to evacuate if needed. That could have a huge impact on safety, reducing damage. For flash floods especially, they're notoriously tricky because they happen so locally, so quickly. AI could be a real game changer, identifying high-risk areas based on real-time rainfall and maybe terrain data.
And this all connects back to the sheer computing power we need now, right? To process all that data, run these complex AI models.
Precisely. The exponential growth we've seen in computing power is the key enabler here. It allows us to handle these vast quantities of data, run these incredibly complex machine learning models, and ultimately generate forecasts that are more accurate, more detailed, and more timely.
So it becomes this dynamic system that's always learning, always improving.
That's the goal. A system that learns from every new weather event, refines its predictions, and ultimately helps us make better decisions and stay safer.
It really puts a whole new perspective on just seeing that little sun or cloud icon on my phone forecast.
Doesn't it?
It represents this incredible confluence of science and technology all working together right now.
That's a perfect way to put it. That's a key takeaway, I think.
Yeah.
What we see as a simple weather update is actually the end result of this huge ongoing collaboration. Cutting-edge science, advanced technology, and, importantly, the dedicated expertise of meteorologists, data scientists, engineers.
So ultimately, all of this, the real-time monitoring, the nowcasting we talked about, the future potential of AI, it all seems to boil down to a pretty fundamental goal, doesn't it? Helping people live better, plan smarter.
And stay safe.
And stay safe, yeah, when the weather gets unpredictable.
Exactly. It's about harnessing all this power observation, analysis, prediction to mitigate the risks that come with bad weather and empower individuals, communities, businesses to make informed choices. Hopefully, after this deep dive, the next time you check the weather, you'll have a much richer appreciation for the sheer effort and complexity behind that forecast.
Absolutely. It's been truly fascinating, really getting into the weeds of real-time weather decisions. I hope you listening feel like you've got a clearer picture now of what's happening up there and how that info gets to you.
Yeah, we certainly hope so. And maybe next time you hear that thunder rumble or get a weather alert on your phone, just take a second to think about the incredible tech and the dedicated people working behind the scenes.
Keeping us informed, keeping us safe. It really makes you think, though, doesn't it? What other seemingly simple things in our daily lives are actually built on top of similarly complex collaborative systems working away behind the scenes? That's definitely something to mull over. Thanks so much for joining us on this deep dive.